So we arrived at Newton's 3 laws of motion, which in a nutshell look just like this. All right, so one at a time. Actually, we already talked about Newton's first law of motion that takes us back to Galileo Galilei's experiments. They both realized that an object moves at constant velocity unless there is a net force that acts on it to change its speed or direction, right? Which is the velocity. Or also the momentum. If you multiply by the mass, right? You get the momentum. All right, so any examples? Oh, and before we actually move on, right? So constant velocity can also be at rest, right? Speed is 0, there is no direction. Direction is 0 if you want, right? So it could be at rest or constant velocity. That state of motion is not going to change unless there is a force that acts upon that object. Here's an example. A spaceship which will continue moving in space in the direction it is moving, okay, without the need of any fuel, okay, no fuel needed, okay, and that spaceship continues to move. In order to change direction, it needs to be a force that acts upon it. In order to stop, it's going to need to be a force that acts upon it. All right. A second law of motion. We already again talked about it. We just didn't call it the second law of motion. That says the force is the product between the mass and the acceleration. Or F equals ma. That comes from the fact that a change in the momentum, right, means you have actually a change in velocity, which gives you the acceleration. And whatever produces the change in the momentum is the force. All right, so among other things that this law explains is, for example, why the baseball player can apply a force, the same force, for example, to a baseball, right, which is going to travel much further than, for example, a shot put, right, because the latter has a much larger mass and therefore will have, right, so if this is larger, then for the same force, this is going to be smaller, right? So the baseball will have smaller mass, therefore the acceleration will be higher for same force. So one example, all right? The third law of motion by Newton says that for every force there is always an equal and opposite reaction force. And we have this example in which the rocket is propelled upward because it's pushed by a force that is opposite to the force, right? So that is opposite to the force with which gas is expelled out. It's back. So that's it. Let's explore these things a little bit. Well, first of all, it looks like it is important to be able to identify situations when there is a net force or not. Okay, so here are some examples. A car coming to a stop. Do we have a net force? It looks like there is a change in speed, right? Not a change in direction. We don't have any information about that. So that means there is an acceleration. Therefore, yes, net force. All right. How about a bus speeding up? Pretty much the same idea. So we have a big yes, right? The speed changes, it increases, even though we don't have any information about the direction, right? So the speed changes, therefore the velocity changes, therefore there is an acceleration, and that means because the bus has a mass, we have a net force. How about an acceleration moving up at constant speed? All right, so constant speed, right? How about the direction? It's moving up, it doesn't change direction, so there is no change in velocity. That means the acceleration is 0. That means net force is 0. So no force here. All right, how about a bicycle going around the curve? And I should have added here at constant speed, just to make it even more challenging, the situation. So going around the curve, that means direction changes. So even if it's going at constant speed, you are going to have a change in velocity, so the acceleration is there. It's not 0, so yes, net force. All right. Now, how about the moon? A moon orbiting Jupiter. Okay, if it's orbiting, that means changes direction. That means there is an acceleration that is not 0, so yes, net force. Which force is that? The force of gravity. That keeps that moon orbiting Jupiter. Interesting, isn't it? Here's another question. How does the force the Earth exerts on you compare with the force you exert on it? So this is the Earth, and you're here. You are here, and this is the center of the Earth. So there is a force that Earth exerts on you, and then there is this force that you exert on Earth. How do you think these two forces compare with one another? Do you think one is larger than the other? If it's so, which one is larger? So think about it. The truth is, and that is explained and is dictated actually by Newton's third law, that says Earth and you exert equal and opposite forces on each other. Which one is that force? Newton figured that out. All right, so here is the force. It's given by the law of universal gravitation, that says two objects attract each other with a force that is directly proportional to the mass of each object and inversely proportional to the square of the distance between them. So it kind of looks like this. We have mass 1, a different type. We have mass 2. There is a distance between them, and that is r. And it turns out that on mass 1 there is a force of attraction that is m2 exerted by m2, so m2 on m1, and then there is this force that acts on m2 that is exerted by m1, so it's going to be m1 on m2, and guess what, they both equal to this one, right? Because they're both going to have the same formula. So we have F m1 on m2, and that is the same as the force that m2 exerts on m1. It's actually pretty easy to see that it's not going to matter whether you have m1 times m2 or first m2 times m1. So yeah, it was Newton who figured this out, m1 and 2 being the masses of first and second object, r is the distance between these objects, and Newton realized that any two masses, you would calculate that force of gravitational attraction in between them, you end up with a constant. It's a constant. It has the same value for every single pair of objects, whether you talk about you and a glass of water, whether you talk about you and me, whether you talk about you and Earth, or you and the moon, or just any pair of objects out there. Let's see if we can understand better that formula. So this problem, very similar, I am pretty sure, with some of the problems you're going to find in homework, maybe the exam as well. So it says the following. If the radius of the Earth were to double with no change in its mass, a person's weight would A, be unchanged, or B, increased by a factor of 4, or decreased by a factor of 4, or double, or be cut in half. How are you going to figure that out? First of all, let's think about it. So we have you on the surface of the Earth. All right? This is the Earth. This is the center of the Earth. This is you. And I'm not going to draw you with a skirt or anything, okay? And there are these forces, right, that we already learned about. So this is Earth's center, okay? This is you. Those forces are equal to one another. F is given by this formula G, M, U, okay? And Earth, that's going to be the big M. So instead of having F, G, M1, M2 over R squared, and this is R, okay? We are going to have, right, so M1 is M, M2, a small m and a big M, right, and then we have R squared. Now, what does it say? The radius of the Earth is going to double. So what's going to happen to the person's weight? This is the weight. It's the force of attraction by Earth. Okay, remember that? We learned about that. All right, so the new force, what is that going to be looking like? So it's pretty much like the old force with the same masses, okay? Nothing is said in the problem about any change for those masses, but it says the radius doubles. So we're going to have 2 times the old radius, right? So that's the new distance. It's going to be squared. Okay, so let's distribute that power. So this is going to look like this. Small m, capital M, and then we have 2 squared, which is going to be 4 times R squared. Now, because the multiplication is commutative, this is going to look like 1 over 4, right? So we're just going to take this outside. So it's going to be 1 over 4, and then whatever is left behind, G, M over R squared. And this is what we found here. this is old force. So what did we find? This is 1/4 times old force. So what happened? The new force, or the new weight, is now 4 times smaller. So the correct answer is this one. This is how you should think about answering problems like this. All right, how about the units? Any force is measured in newtons. Guess what was discovered? This concept of a force was discovered by Newton, so why not? You probably recall mass is measured in kilograms, distance, better convert any one of the lengths or distances in meter in formulae like this, and with all those values, if you calculate actually the universal gravitational constant, that has this value 10 to the minus 11 is here, and we have meter squared and kilogram squared, right? Sorry for that. All right, so let's, if I were to write again, 6.67 times 10 to the minus 11, and we have Newton, times meter squared divided by kilogram squared. So those are going to be the units you're going to have to plug in the formula just to make sure you you have the correct answer. So here's an example, and we have a kind of a fat little professor, about 100 kilograms, right? Make sure you actually convert the pounds into kilograms if you need to do this kind of calculations in the homework. So that's one object, and the other one is a glass of water. It's already in kilograms. How about the distance between them? It seems to be in centimeters, so better convert that into meters. That's going to be 0.5 meters, and you see how that's going to show up here. And then you plug in everything and you get this many newtons for the force of attraction between right, so this is for the example, and then Earth and you, and just, I don't know, estimate, so I don't know, like 50 kilograms, maybe 75, I don't know, one of those. Just put it in, you're gonna get at least that order of magnitude for the force. That is your weight, right? So this is the weight. So what's this gravitational law and Newton's third law? What are they useful for? Well, here this, okay, so the gravity acts as an attractive force, pulling two objects together. It turns out that is actually the force, the net force that is applied continuously on a planet that orbits around the sun, for example, or for say satellites of Jupiter, or many other things. Why? Because if that force were not there, then that planet would continue in a straight line, right? Because if the force is not, if there is no net force, then the velocity will not change, and therefore the direction will not change and the speed will not change. So it must be a net force that acts upon things that orbit, like things that are in orbit around the sun or around planets or anything like that, right? So this is simply said by the first law. Okay, how about the second law? The second law tells us that since gravity provides an acceleration, okay, then the object's velocity will always change, right? So that's kind of it's kind of the equivalent of this, right? It changes. So we have gravity, right? It's a force that provides an acceleration to an object velocity change. Most of the time, the direction of motion changes. Speed can change too. All right. Okay. The third law tells us that both bodies must experience gravitational forces. Well, what can you say about the sun, right? The sun doesn't move anywhere, right? So you have planet, you have sun, this is Earth, or we can do the same experiment with Mars as well, okay? So the Earth moves because of gravitational force. But what about the sun? The sun doesn't move. And yet, there must be a force, right? Both bodies are experiencing gravitational forces. All right, this is the conclusion, and it's actually true. The sun must be altering its motion because of the gravitational pull of the planet. And here is the proof, all right? This is, for example, the center of the sun in 1980. This is the center of the sun in 1960. This is the center of the sun in 1985, right? So, center of the sun. Center of the sun. You see, the sun actually is moving. It's just moving very little, okay? Because the acceleration is actually very small, right? So it's the same force, but you have a huge mass, right? And therefore, the acceleration will be small. Small, just not zero. Oh. So, there is more to say about Newton's law of gravity that actually extends beautifully Kepler's laws. So remember Kepler's law that says, or the first one says all the orbits are actually not circles, they are ellipses. Well, it turns out ellipses are not the only orbital paths that can exist out there. They can also be unbound, and there are parabolas and hyperbolas, and guess what? There are actually comets that exist in this kind of orbits, okay? Comets that just come once very close to the sun and then just go, and they're lost forever in space. All right, there are comets that are in bound orbits and so on. So, you know, the things that we see in orbits are just some particular case of the gravitational bound that the sun has on the things in the solar system. Interesting. And remember that Kepler's third law that said p squared is a cubed. P was the period, which was measured in years, and the a was the average distance or radius, if you want, in the orbit, okay? And that was in astronomical units. Now, Newton found, you have Newton's version, found through his calculations that actually this relationship is much more general, and it can apply to anything that can orbit anything else, not just for things that orbit the sun. So this is true only for these particular units, years, and astronomical units, and therefore true only for things orbiting the sun. This is a lot more general, most general, and it applies to any things that orbit around anything else. So this could be a little m, say mass of a satellite of Jupiter, and this would be the mass of Jupiter, right? And then you have the mass of the things, the thing around which the satellite orbits plus the mass of the satellite, right? So you see, the formulae are very, very similar, right? Except that this is obviously more general, and in this case, everything is measured in the International System of Units. So the period is going to be in seconds, and the semi-major axis, or the average distance, is going to be in meters. Actually, this is very, very important. There is something even more important than that, is that, you know, you look in the sky, you make some measurements, and it's actually fairly easy to measure the orbital period, to measure the average orbital distance between those two things that you observe. So these are easily measurable. What's very hard to measure is the masses. Right? Because you just can't go with the balance beam and say, hey Jupiter, sit here, I'm just going to measure your mass. But with this formula, this Newton's general, most general version of Kepler's third law, we are able to solve for the masses. We can actually, that's the main way actually we weigh things in space, right? So very interestingly, these things you measure and then you calculate the masses. That is an amazing tool. This Newton's version of Kepler's third law is an amazing tool to measure masses, to calculate masses. All right, so very important. We have a tool to estimate or calculate masses. Without this, we wouldn't know just how much matter is in the sun. We wouldn't know how much matter is in Jupiter. We wouldn't know how much matter is in the universe, period.